All right, we want to talk about section 4.5, tangential and radial acceleration. So let's first be very explicit in how we define tangential and radial. So if we have a circle, radial is outward from the center, right? Along some radius line, right? If we were to define a radius, that would be the distance from the center to the surface. So just any ray out from the center. If we look at tangential, that means a tangent line, so it intersects the surface at one point. But for a circle, that means that it's going to be perpendicular to a radial line. So that's useful because now we can talk about two perpendicular vectors and add them. So if we have a radial acceleration and a tangential acceleration, our total acceleration then is the square root of the sum of the squares. So these are set up nicely like a coordinate system, right? A polar coordinate system. If we're moving in a circle, we can find the radial acceleration. So we've talked about centripetal acceleration in terms of uniform circular motion. So we're no longer talking about uniform circular motion because we have a tangential acceleration. We're not moving at constant speed. It's no longer uniform. But we can use the instantaneous velocity to figure out what the centripetal acceleration is instantaneously. And it's the same. We're just going to use that instantaneous value to figure it out. We can do kinematics along the surface to figure out what the tangential value is. If I know how the velocity is changing, then I know how, if I know how the magnitude of the velocity is changing, then I can talk about the tangential acceleration. We'll just say kinematics for this right now to figure those two out. And then we could look at the total. So if I have a real situation here, let's say we have a car driving over a hill. And that hill has some curvature to it that we can represent by some radius of curvature. And if this car is accelerating along the road at the same time that it's going over a hill, well, going over this hill, we know that there's some centripetal acceleration, in this case provided by gravity, and a mismatch between the gravity and the normal force of the road. Then there'll be some total acceleration that's the vector sum of those. So if we were going down a hill, right, then we would have some radius of curvature associated with that we would generate above the hill instead of under it, right? So we're going through a valley here. If we were to look at a car there, well, now your centripetal acceleration would be upward. Here, again, a mismatch between gravity and the normal force, but now the normal force is winning. So you feel like you're being pushed into the ground instead of floating out of your seat, right? And if we're still accelerating tangentially, we would end up with some total acceleration like this. Not a lot to talk about for this section because we haven't talked about forces yet. Once we talk about forces and angular kinematics, we'll do a lot more.